Download this code from codegive.com, link in the description below. OK, let's dive into interprocedural data flow analysis, specifically focusing on the concepts often covered in a lecture like Mod 20 LEC 38, which typically means it's part of an advanced compiler or static analysis course. This is a complex topic, so we'll break it down step by step with explanations and a simplified code example. What is interprocedural data flow analysis? Interprocedural data flow analysis is a static analysis technique that extends traditional, intraprocedural, data flow analysis by considering the flow of data across procedure, function, method, boundaries. In other words, it aims to understand how the behavior of one function influences the behavior of other functions that call it, and vice versa. This is crucial for detecting errors and optimizing code in programs that use function calls extensively, which is the norm in modern programming. Why is interprocedural analysis necessary? Intraprocedural analysis, analyzing each function in isolation, is often insufficient for several reasons. Missing context. Intraprocedural analysis doesn't know where a function is called from or with what arguments. This can lead to overly conservative, pessimistic, analysis results. Side effects. Functions can modify global variables, pass data through arguments, call by value, call by reference, and return values. These effects can be invisible to intraprocedural analysis if they occur in a different function. Call graphs. The interaction between functions forms a call graph. Understanding this graph is fundamental to tracking data flow across procedures. Challenges of interprocedural analysis. Interprocedural analysis is significantly more challenging than intraprocedural analysis. Scale. Real-world programs often have a vast number of functions and function calls. Analyzing all possible call paths can be computationally expensive. Call graph construction. Dynamically dispatched calls, virtual functions in object-oriented languages, function pointers in C/C++, make it difficult to construct a precise call graph statically. You might need to approximate the possible call targets. Context sensitivity. The behavior of a function might depend on the context in which it's called. A function might have different effects depending on the values of its arguments or the state of the program at the call site. Data representation. Representing the state of the program across function calls and returns can be complex, especially when dealing with data structures and aliasing. Key concepts and techniques. 1. Call graph. A directed graph where nodes represent functions, procedures, and edges represent call relationships. An edge from function A to function B means a calls B. Construction. Can be static, based on the source code, or dynamic, during program execution. Static call graph construction can be challenging due to function pointers and dynamic dispatch. Approximation is often needed. Importance. Provides a framework for tracing data flow across function boundaries. 2. Interprocedural control flow graph, ICFG. Extends the traditional control flow graph, CFG, to include call and return nodes. Call node. Represents a function call. Return node. Represents the return from a function. Edges connect call nodes to the entry nodes of the called functions, and exit nodes of the called functions to the corresponding return nodes. 3. Context sensitivity. A crucial aspect of interprocedural analysis. It determines how precisely the analysis accounts for the calling context of a function. Context-insensitive analysis. Treats all calls to a function as having the same context. This is the simplest but least precise approach. Asterisk context-sensitive analysis asterisk distinguishes between different call sites to a function. This can be more precise but also more computationally expensive. Common types. Asterisk call string approach asterisk uses a limited call string, sequence of call sites, to represent the context. Asterisk object sensitivity asterisk uses the object the method is called on to differentiate the contexts. Asterisk k limiting asterisk limits the length of the call strings to a fixed value k to control complexity. For interprocedural data flow equations asterisk similar to intraprocedural data flow equations, but extended to handle calls and returns. In B the data flow information entering block B. Out B the data flow information leaving block B. Gen B data flow information generated within block B. Kill B data flow information killed within block B. Call nodes out call underscore node equals transfer underscore call, in call underscore node. The transfer underscore call function models the effect of the call, example passing arguments. Return nodes in return underscore node equals transfer underscore return, out called underscore function underscore exit underscore node. The transfer underscore return function models the effect of the return, example returning a value. 5 Summary-based approaches compute summaries of the effects of functions, which can then be used at call sites without reanalyzing the function. Example compute the set of global variables that a function might modify. Can improve efficiency but might lose precision. 6 IFDS/IDE frameworks Interprocedural finite distributive subset/environment problems are a formal framework for expressing a large class of interprocedural data flow problems. It is particularly effective for linear constant propagation and pointer analysis. Requires the data flow problem to be distributive, meaning that the data flow operations distribute over the meet operator. Offers efficient algorithms for solving these problems. A simplified code example, constant propagation. Let's illustrate with a very basic example of interprocedural constant propagation. We'll simplify things to focus on the core concepts. We'll use Python to represent the code and data flow analysis. Explanation of the code One node and function classes represent basic blocks and functions in the code. 2 Analyze underscore intraprocedural performs constant propagation within a single function. It iteratively updates the in underscore state and out underscore state of each node based on the gen and kill sets, until a fixed point is reached, no more changes. This is a standard iterative data flow analysis algorithm. It uses a very basic linear control flow graph, each node has only one successor. 3 Transfer underscore call simulates the effect of a function call by mapping actual parameters to formal parameters. It assumes call by value semantics. The current state of the calling function at the point of the call is used to initialize the callee state. 4 Transfer underscore return simulates the effect of a function return by propagating the out underscore state of the called function's exit node back to the call site. 5 Analyze underscore interprocedural first performs intraprocedural analysis on each function to get an initial estimate. Then, iteratively traverses the call graph. For each call site, simulates parameter passing using transfer underscore call. Reanalyzes the called function, because its in underscore state might have changed. Simulates the return using transfer underscore return. Checks if the out underscore state of the call node has changed. If so, sets changed equals true to continue the iteration. 6. Call graph and example code *. The call_graph dictionary represents the call relationships between the functions. The example code is very simple, but it illustrates the basic flow of data. 7. NAC, not a constant in the analyze_intraprocedural function. The meet operator sets the value to NAC when two predecessors have different values for the same variable. This indicates that the variable might not be constant. How the analysis works *. 1. Initialization *. The intraprocedural analysis runs on main and foo, establishing some initial constant values, example x equals 5 in main. 2. Iteration *. The analyze_interprocedural function iterates through the call graph. The first time the call to foo is encountered. *transfer_call maps x, value 5, in main to a in foo. *foo is reanalyzed, knowing that a equals 5. *transfer_return propagates the results back to main. 3. Fixed point *. The process continues until no more constant values can be discovered or refined. Limitations of this example *. Extremely simplified *. This is a toy example. Real-world code is much more complex. Call by value only *. Doesn't handle call by reference or pointers. No return values * doesn't explicitly handle return values from functions, although the exit state is propagated back. Context insensitive * treats all calls to a function as having the same context. Simple data flow * only constant propagation. No aliasing * doesn't handle aliasing, multiple names referring to the same memory location. Linear control flow * assumes a very basic CFG structure. Going further, topics for Mod 20 LEC 38. A lecture like Mod 20 LEC 38 would likely delve into these more advanced topics. Context sensitivity * implementing call string context sensitivity, k-limiting. Points to analysis * interprocedural pointer analysis, identifying what memory locations a pointer might point to. This is essential for reasoning about memory access and side effects. Alias analysis * determining when two variables might refer to the same memory location. Shape analysis * analyzing the shapes of data structures, lists, trees, etc., to detect memory errors. Interprocedural data flow frameworks * exploring frameworks like IFDS/IDE for more efficiently solving interprocedural data flow problems. Demand-driven analysis * performing analysis only on the parts of the program that are relevant to a specific query, example can this variable ever be null? Handling recursion * special techniques are needed to analyze recursive functions in interprocedural analysis. Dynamic dispatch * strategies for resolving dynamic method calls in object-oriented languages. Call graph construction becomes more involved. Scalability * techniques for making interprocedural analysis practical for large programs, example summarization, partitioning. Applications * the use of interprocedural analysis for bug detection, example null pointer dereference, memory leaks, security vulnerabilities, and program optimization. Key takeaways * Interprocedural data flow analysis is a powerful but complex technique for understanding the behavior of programs across function boundaries. It is essential for detecting errors and optimizing code in modern software. While the basic concepts are relatively straightforward, the challenges of scale, context sensitivity, and data representation make it a rich area of research and development. The code example provides a starting point for understanding the fundamentals, but real-world implementations require much more sophisticated algorithms and data structures.